It's my great pleasure to introduce you to Pierre Roux, visiting from Onera in Toulouse. It's the French aerospace lab, the French Aerospace Research Lab. And Pierre is working on static analysis for control command software and other flight control systems and so on. And so he's going to introduce you to his latest research. And thank you for coming.
Thank you, Taina. So yeah, as Taina said, just a few words about my lab. It's kind of a French national lab for aerospace, like the aeronautical part of NASA, so not launching any rocket or anything like that, operating wind tunnels. But so most people there are physicists, but there are a few computer scientists doing, among other things, some formal methods and so on. And so among them, I'm interested in formal method for numerical computations, and with an application, if possible, to control commands and so on. So feel free to interrupt me if there are questions during the talk, because I may say a lot of things, so maybe sometimes. So what's a control command system? I'm a computer scientist, not at all a control theorist, so hope I won't tell too much stupid things about the topic. But there is something we want to control. Control theorists call it a plant usually, so let's say a plane, for instance. And we have some input, some commands. So for instance, the side seek of the first officer here. And so we have a lot of sensors on the plane, so we get some information. And we can act on some actuators to pilot the plane. And so in between, we put a piece of software called the controller. And basically, this is not the controller of the plane, of course. When you look at the code of these kind of things, it's a mess around this. But at the heart, you get something like that. It's something that is executed periodically. So let's say every 10 milliseconds, for instance, which is about the times used for that plane. And so every 10 milliseconds, you acquire some input. So you read the sensors. You do some computation to update some internal state, and you output something to the actuators. Then there is some physical back loop and so on every 10 milliseconds. So usually when we do static analysis, we tend to use linear invariants because it works well and it's easy to manipulate and so on. But unfortunately for this kind of systems, control theorists know that, well, at best, it can be costly, and well, sometimes at worst, if you are unlucky, you won't get any result. So for instance, here, some very simple linear invariant, just a box. We have two variables, x0 and x1. We bound them, and we apply some linear transformation, so a small rotation, followed by a scaling of factor a bit less than 1. So it should be contracting. But here in the corner, it's not stable. But control theorists know that a good solution for this kind of linear system is to use ellipsoid. Yeah?
So why linear inequalities didn't catch it, or didn't understand what happened?
The thing is that I'm looking for an invariant, so I would like my initial thing after one iteration to be included in the initial one, so that I can prove that.
It's above x1, so I don't understand.
The thing that I'm applying some rotation, so yeah. I rotate it, and at the same time I scale it by something a bit less than 1.
And what do you want to detect?
And I would like to prove that there is some stability. I won't go infinitely far away. If I start from somewhere, I will remain. I will converge towards 0 at the end. Indeed. But at least I won't go very far.
So you're trying to bound some computation. You're trying to put a bound.
Yeah, exactly.
And if the true behavior is more like the thing on the right, then you're going to have your bound is imprecise.
Yeah.
So, but your question is.
I'm kind of understanding.
Related to that.
Let's hear the quadratic part. Why quadratic works?
So here, if I do the same transformation, since I no longer have any corner and it's more round, more or less, it does work. I'm inside the transformation. the small rotation and the scaling is inside of the initial.
Why do you need to be inside?
Because it's not just, it's a rotation. So I turn and then I scale.
He wants to find some kind of bounding region of the system.
So maybe the setting is the setting for your work static analysis, like you want to actually bound the behavior of the code.
Yep.
You want to say you're within some computational envelope.
Yeah, exactly.
And generally, if you use boxes, it's too imprecise. You'll basically say you're outside when you're really not outside, and then you get false alarms.
Yeah.
So that's is that correct?
Exactly. Yeah. That's it.
So you have you're smart on the right, right? Much smarter.
Yeah, we are more precise and
I see.
we manage to capture the fact that it's bounded.
Okay,
Whereas
good.
here we don't.
Mm-hmm.
Because maybe it could go out. And so this is an example of the previous small code implemented in C. And I want to prove that, technical stuff, it's a valid pointer. If this condition is satisfied before executing the code, and if the input is bounded between -1 and 1, then after executing the code, the new value of S still satisfies the invariant. So this is a quadratic invariant. This is a degree 2 polynomial, and this describes an ellipsoid just like we've seen. This is written in the Excel specification language for C. So this is this code, and I can run the tool FramaC and Y3 to generate verification conditions that I will run to SMT solver and try to get a proof. So I get these verification conditions. This is basically if the input is between -1 and 1, and if the invariant did hold after applying the thing, the invariant still holds. And I run state-of-the-art SMT solvers, these three and Alt-Ergo. I could run others, but with a timeout of 10 seconds, and I get the timeout. And then I see how we manage to modify Alt-Ergo to be able to prove this kind of things. So that will be the remaining of the talk, basically. So in this talk, I will try to explain how we can generate this kind of polynomial invariants. Then we see that these raise some soundness questions. So how could we address them? The tool we will be using will be a floating point arithmetic. So we have to be smart in the use of it to get rigorous results. Yeah.
So on the previous slide, was that real arithmetic or floating point arithmetic?
No, it's real arithmetic. Yeah, this is a real arithmetic multiplication zone. So I'm incorrect on this. You're right. We should work on it. It's not yet done. That's right. No, I will only be using floating point arithmetic within my proofs, but not about the programming problem. That's right. And then I'll present you how we integrate this in an SMT solver, and we also have a fully verified implementation in Cox. About that. So how do we synthesize such invariants? We get this kind of program, so reading some input that we assume is bounded, and computing some function, we call it f, and we want a polynomial p such that if p is non-negative before applying f, then p of f and the input that is bounded remains non-negative, basically. And we can encode it like that. So p has to be non-negative for the initial point x0. And if the input is between -1 and 1, then the input squared is less than 1, so this is non-negative. If we assume p is also non-negative, then p at point f is also non-negative if we satisfy this inequality. So we are looking for polynomial p and also this sigma variable that satisfy some non-negativity conditions on polynomials. So if we had a way to solve this polynomial problem, we would get an invariant. And a tool to get non-negative conditions on polynomials is to express them as sum of squares. The square in the real number is non-negative. The sum of non-negative things remains non-negative. So if you manage to express a polynomial as a sum of squares of polynomials, it will be non-negative. The reverse is not exactly true, but in practice there are some continuity theorems, and it does work. But we only need, for correctness, we only need to know that if we can express p as a sum of squares, then it is non-negative. And the nice thing is that P is the sum of square. If only if I can write it like that, that is the product of a vector with all the monomials I need on the left and right, and some matrices in the middle that is positive semidefinite. So just recall a matrix is positive semidefinite if and only if when I multiply it by any vector on the left and right, the scalar I get is non-negative. Or you can also say that all eigenvalues are non-negative. There are many. And the nice thing is that a bunch of linear equalities plus the constraints that the matrix is positive semidefinite is what we call a semi-definite program, and it's known how to numerically solve them. So we can encode our problem as a semi-definite program, call some semi-definite programming solver, and get an answer, basically. That's the basic idea. Just an example to try to make the thing a bit more concrete. A polynomial of two variables here, so 2x to the 4 and so on. Don't know for you, but for me it's not perfectly obvious that this is non-negative. If I manage to prove that this polynomial is the sum of square, I would have a proof that it's non-negative. So let's try. Let's write this polynomial as a product of a matrix multiplied on left and right by the vector of the monomials I need. Here xy, y square, and x square. If I expand this, I get this. This is the same thing, just I expanded the matrix multiplication. And so we can know that Q11 has to be 2 and so on. This is a set of linear equalities. And I want the matrix to be positive definite. I call some SDP solver. And then say I got this answer. This matrix Q is positive semidefinite and satisfies all the constraints. It happens that I can decompose this matrix as this. And in the end, I get this expression for the polynomial. So now it's easy to check that the polynomial on the first line and this one are the exact same. Just expand everything and check that it matches. But now it's perfectly obvious that this polynomial is non-negative. So this is the way to get a proof. And here the polynomial is constant, but we could get parameters in int and solve on the parameters. That's what we do to get polynomial invariant. Well, I say we, but control theorists are doing it for long. So we see that we get some soundness issue with that. So this is an example taken from some paper. And people said that take this program, and this is an inductive invariant for this program. Why should we trust that? It would be nice if it were true. I agree. Well, we'll see later how we can prove this kind of results. But for this one, indeed, it's incorrect. So this is the gray area is the set of x1 and x2 that satisfy this constraint. And I took some points and applied the body of the loop on this point, and we see that in some cases we are exiting the gray area. So the gray area is not an inductive invariant. Maybe an invariant, but not inductive. So it's not really a proof that the behavior of the program is bounded. So we have to be careful when using this kind of tool, because it's pretty easy, even for people that are used to them, to get completely garbage out of it. So just trying to get an intuition of why we can get this kind of imprecise results out of the tools. I'll do a comparison with linear programming. In linear programming, to solve a linear program, you get two competing algorithms, the simplex and interior points algorithms. Sometimes one will be faster than the other, and vice versa. It's hard to know when. The idea of the simplex is to wonder on all the vertices of the polyhedra you're trying to optimize on it. And at some point, you will get on one of the vertices an optimal value, and you're done. And so when you stop, you get an exact solution. If you manage to implement the thing with some exact arithmetic, like rationals, for instance. And that's what is done in all SMT solvers in practice. And for interior points, the idea is quite different. You don't wander on the edge of the polyhedra, but you start from some point and you optimize while remaining in the interior of the polyhedra. And at some point you say, well, okay, I'm close enough from some optimal value. I stop here and I keep this value. So I get an approximate solution only. And for semi-definite programming, unfortunately, there is nothing like the simplex. And we still get interior point algorithm. So all semi-definite programming solvers more or less apply some interior point algorithm. So by the algorithm they use, they will give you some approximate answer. It cannot be exact. Don't try to implement it with rational arithmetic or anything. It will still be inexact due to the algorithm. And why we don't get any simplex? Well, because we lose the properties that the optimal lies on a vertex. Because when you are optimizing no longer on polyhedra but on spectrohedra, more or less to get an ID, the edges can be round. So the optimal is no longer necessarily on a vertex, but can be in the middle of a face. So nothing like the simplex. Forget about it, unfortunately. So we are left with the interior point and approximate solution, basically, just to try to explain. So yeah, in terms of verification, we can't forget about completeness, which we had with the simplex. And about soundness, yeah, we'll see it's feasible, but we have to be careful. So that's the remaining of the talk. How do we ensure soundness? So as I said, for sum of squares, what we try to do is to take a polynomial and express it as a sum of squares, or equivalently as this product, a positive semi-definite matrix multiplied by the vector of monomial on left and right. And instead of getting the exact equality, we get equality with some error term that is non-zero. But the error term can be bounded, and we will work on it. So if you look in the literature, you will see two validation methods. First one is to try to take the approximate answer and try to round it to some rational solution, for instance, or something like that, and hope to get an exact answer, and just check that the matrix you get is actually semi-definite positive. So the rounding is completely heuristic, of course, but sometimes it works, so it's nice. And usually the check is done with rational arithmetic, which is exact but expensive. The coefficient during the computation can blow up, and it can be terribly expensive, like exponential. On the other hand, another solution is to bound the error term and prove that any matrix Q plus some small e is positive semi-definite, whatever the value of e, as soon as it's bounded. And if we want, we can do it entirely with floating point arithmetic, and it will be fast. So I'll explain that later. So just to try to get some intuition of what's happening, I'm looking for...
Sorry,
yeah.
in the last case, you said that it's method precise.
I don't claim any precision. I will just prove that it's correct and rigorous. But
it's sound.
it's sound, yeah.
Oh, okay.
That's what I will prove. Mm-hmm. It can be sound if we do it well. That will be later explained. So we are looking for some matrix that satisfies some equality constraints. So I will depict it as a line. I want to be on the line. And the matrix also has to be positive semi-definite. So I want it to be in the light blue area, basically. So I want to prove that there is a point both on the line and in the light blue area. That's what I want to do. I ask my solver, and it answers something that is not quite on the line and hopefully is on the light blue area. So what we do is to compute the distance between this point and the line, and we will try to prove that the ball with this radius around Q is entirely inside the light blue area, in which case we indeed have a solution since the ball intersects the line. And if the ball is entirely in the light blue area, there is at least one point on the line that is in the light blue area. Of course, there are configurations in which we cannot conclude because the ball is too large or the point is too close from the border of the cone of positive definite matrices, or simply because there is no solution. But we cannot distinguish between these two cases. But if we are in these cases, we have a proof and we are done. We have a proof that our polynomial is a sum of squares, so it's positive, non-negative at least. So how do we manage? Because if we optimize something, usually the optimum will be on the edge, so we get something close from the edge, and that's bad, because we get this kind of situations. So we want something far enough from the edge, so we just ask the solver, hey, don't give me just a matrix that is positively definite, but give it in a slightly smaller cone, so that I'm far enough from the edge. And the nice thing is that for sum of square problem, this, the value of this can be pre-computed with a reasonable accuracy. So we manage to ask the good problem to the solver so that we get a solution that is not too close from the edge and that will work if there is some solution in the interior of the thing. So, so now I still have to prove that a matrix is positively finite. How do we do that? We see that later. And I said we will be using floating point arithmetic, so I have to introduce a few fundamentals about floating point arithmetic and how we can bound the rounding errors on this, and so on. So just a few words about floating point arithmetic. A floating point number, it's quite simple, is the product of some mantissa, some digits, and some base up to an exponent. Basically, is that what we are doing when we do physics. We compute with 4 figures or 5 figures, and we keep 5 figures along all the computation and forget everything that is beyond the 5 figures. That's floating point arithmetic, basically. So since we want to encode it on a finite number of bits on the computer, the mantissa only uses a finite number of figures. And also the exponent is bounded, so it's bounded below and also above. Let's forget about the upper bound. You will get overflows, but forget about overflow for now. We can handle them later. We can decouple the things. But underflows are things that happen when the exponent becomes really small. That is when the value, so if e is very small, the value is close from 0. And close from 0, we have some special values that we call denormalized numbers. And here we lose precision. The exponent reaches the minimum value, and so either when you are stuck at this minimum value, you can go directly to 0, put m to 0, or use less figures in m to get smaller values and not get to 0 too abruptly. Well, forget about the details. Just to explain later why we would have some term, but if you're not into it, forget. And to carry our later proof, we will use a simpler model called sometimes standard model of floating point arithmetic. And it just basically says that if you want to do, for instance, an addition, the addition in floating point arithmetic, the result you will get, is the result of the addition in the real numbers. And then it's rounded, so instead of getting these exact results, you get something close, and the difference is bounded. You get some small errors. And for multiplication or division, it's about the same, but since you can get these very tiny numbers, denormalized numbers, you also get some absolute error term, but this is usually really tiny, but it's here, so we cannot forget it. But yeah, think at this as being really tiny, and it's here, it's painful, but it's not really important. The important thing is the relative error here. And as an example, if you use a binary 64 format defined in the I3, 7, and 54 standard, that's the usual implementation of double in C, so what you would use probably most often. The relative error here is about 16 digits, so it's like working with 16 digits. And the absolute error here is like after 300 digits or more, so just to say that this is really tiny, basically to get an idea of the constant. And so we can use it to bound the errors that are accumulated along more complex computations. So here is a really simple example. It's a sum. You take a set of real numbers, you round them to floating point numbers, and you add them. So let's say from left to right, because of course it would be, the addition is not associative in floating point arithmetic. If you forget something in the first addition, well, forget about it. Let's say it's done from left to right, but it's true in any other order. So this is a result computed with floating point arithmetic. This is a result computed with real numbers. Well, not computed actually, but you will get in real numbers. So the difference is the error you will get on your entire computation, and you can bound it, basically, by something that is basically n times the basic relative error. So it's quite natural. You are doing n minus 1 sums, and there is a rounding here from real numbers to floating point numbers, so you are basically accumulating n operations, so you are doing n times the basic error, more or less. And this term is really small. It's due to when you do a rounding, if it were close from 0, you would get an absolute error, because the value is really, really tiny, and your smallest representable floating point number is much larger. You cannot get a relative error. It will be absolute. But this is really small. It's only around 0. And we managed to prove this kind of result in Coq based on the model of floating point numbers that comes from this library, developed for a few decades by people that are knowledgeable more than us in floating point numbers. So we hope their model is good enough compared to the I3 standard. And so now, our initial goal was to prove that matrices are positively finite. How do we do that? Just take a comparison. If you take a real number, let's say A, and you want to prove that A is non-negative, a way to do it is to express A as a square. And since a square of the real number is not negative, and typically you will take the square root of A. And basically, you can do that's also what we did more or less for polynomials. You can do the same thing for matrices. A matrices is non-negative if and only if you can express it as not exactly a square. You have to transpose the first matrix, but it's almost a square. And it turns out that it's not the square root here, but we have an algorithm to compute this kind of square root, R. This is called a Cholesky decomposition. Here it is. Don't look at the details, but basically it's 3 nested loops, and we are doing numerical computations with divisions and square roots. And if everything goes well, that is, we don't divide by 0 or try to take the square root of something that is negative. At the end, we get some R, and the R we get is a proof that A is positively finite. Yeah?
So how does this relate to the earlier part of the talk where you were kind of inferring a matrix based on some constraints?
Yeah, I will first infer some matrix, okay. And then I want to prove that the matrix inferred is actually a correct one. That is, it will prove that our polynomials are non-negative.
Is that because you don't trust the original?
Yeah, exactly.
Okay, so
and I don't trust it because it is giving some approximate answer by the algorithm used.
Okay.
It's doing some interior point optimization. At the end, it stops with an approximate result. So I want to prove that this approximate result is the correct answer to my initial problem. And then I can use this algorithm. Of course, if I were able to do that with some exact arithmetic, that would be fine. But if you do it using floating point arithmetic because you want to do it quickly, you won't get some exact equality. You will get errors that will accumulate, just like the sum we've just seen. And just like the sum, we can do more or less the same. There are results in the literature like this that proves that if you do your Cholesky decomposition on the matrix A, to which you add some tiny things, and if it succeeds, then your matrix A is actually positive semidefinite, despite the fact that your Cholesky decomposition was computed with floating point arithmetic and performing error. And there is actually a way to compute a reasonable value for this little constant C. It's here. Well, don't look about it. The funny thing, in some sense, is that we get a sound and rigorous result by executing an algorithm that is fundamentally incorrect, which is so much fun. And again, we managed to prove these results in Coq based on the same hypothesis as before. And it's feasible. So how do we integrate
Can you
those?
go back one
Yeah.
second?
Yeah.
What is the epsilon here?
It's the same than before. It's the relative precision of the floating point arithmetic format.
Okay.
So basically, it's 10 minus 16. So this is really small. S is the size of the matrix. This is the trace of the matrix, so the sum of everything on the diagonal. So basically, if all your coefficients in your matrix are more or less around 1, this will be the size of the matrix. This is also the size of the matrix, so this will be S squared times epsilon, and epsilon is 10 to the minus 16, so it's quite small. And this is even smaller because this is 10 to the minus 300. So yeah, this is a really, really small term, but here. And this is an important one.
So what is C like? Can you give me a feeling? 10 in minus 5, like for matrix, let's say 10 by 10.
So this will be 10 times times 10, so 100, times 10 to the minus 16, so it's 10 to the minus 14.
I mean C.
Yeah, C will be around 10 to the minus 14. Since this is 10 to the minus 16.
14, right?
Yeah.
Okay, good.
This is 10, so 10 squared times 10 to the minus 16.
So it's quite small.
It's really small.
Yeah.
Of course, in practice, usually the actual error will be even much smaller, but at least it's a small bound, so it's nice.
So I also have a question.
Yeah.
Compared to you had this previous picture where you were trying to find this this ball around an approximate solution that
Yeah.
intersects with the other constraint.
Yeah.
Are you actually going to find an exact solution?
No.
That you're just going to show the existence of this ball?
Yeah, I just want to show that there exists a solution,
Okay.
but I never compute it.
Okay.
That's
So
really
you
cool.
just want the ball to be inside.
Yeah, exactly. I just want to prove that this ball is inside. Yeah, there is a step I forgot where I take this matrix and I compute another. And I check that this other matrix is positively finite, which guarantees that the interval is. So yeah, I should have. There's a step I kind of forgot to explain. Because of course the algorithm is executed on one matrix, not an interval, so I first have to get a sufficient condition. So how do we integrate this in an SMT solver? So this is a common work with Mohamed Igram Lala from OCaml Pro and Sylvain Conchon from LRI Université Paris Sud. So we integrated this work into their SMT solver, Alt-Ergo. I'm not very proud of it. The way it's done is quite simple. It's just inside the solvers, I have at some point a map from every term in the goal to the interval this term should belong. So we take this map, we construct a polynomial problem such that if this problem is satisfied, then this means that these constraints are unsatisfiable, they don't match. And we ask an SDP solver, and if we get a result that we manage to prove correct, we get a proof that the initial constraints were unsatisfiable. Otherwise, we don't get anything. So it's a one shot. We take everything and try to solve a problem, and there is no incrementality like we could do with the simplex adding constraints one another. We cannot do that. We don't know how to do that efficiently. And the result is mostly Boolean. You get unsat or nothing. It's pretty hard to get more like, this constraint, it's unsat, but this constraint is useless. We tried, but it's not that easy. Yes, there would be things to do, but so it's really a simple integration. It's nothing really smart. And these are the benchmarks. So Alt-Ergo is the original Alt-Ergo. This is our modified version. And this is a version where we only do what I told the approximate solution, trying to prove that the ball is inside the cone. And this is another version where we try the other solution trying to round to an exact solution. And this is combining both, but mostly doing this. And these are other solvers. The one that entered the QFNIA category in the SMT Comp in 2017, I think, if I'm correct. So what we can see is that we are sometimes doing a bit better than Alt-Ergo, but not always. Because sometimes we just spend time computing things and that doesn't work, and so we lose time and a few problems. And all in all, the results are not impressive because we are not as good as other solvers. This was on QFNIA, so integer arithmetic. And on real arithmetic, it's not much better. We are sometimes improving, sometimes not. But yep.
What are the lines? Is it?
Oh, sorry. The lines are categories of problems in the SMT lib.
Okay.
And since we are only able to do proof of ansat and not finding models, we kept only the ones that are known to be ansat or unknown. We remove the ones that are known to be sat.
Do you know where they come from? Is it?
Not really. They are in the SMT lib. The name can give some idea, but no, not very precisely, to be honest. And these are problems that come rather from the kind of problem I've seen in the beginning, so some internal loop of control command program, very simple ones, and trying to prove some quadratic or polynomial invariant. And here we are doing pretty well, and even better than other solvers, as we've seen in the beginning. But so we are able to solve some problems that we weren't able to solve before, but it's not better than other solutions. It's just another thing that maybe we can try sometimes, but we can help.
But you managed to solve almost all of them on this one. Seems like.
Yeah. But these are my problems. So my goal was to solve them. And the reason why we are not that good here is that maybe we could go back to the figure here. So for this solution to work, we need a solution to the problem that is some point on the equality constraint that is in the interior of the cone. If the line comes, well, neither here nor here, but exactly on the edge, there is a single solution, and unless you get this exact solution, you will fail to get a proof. And you could think that this never happens, and actually if you take random problems, it almost never happens. Just like if you take any real numbers, it's almost never zero, so it's invertible. If you take any random matrix, it's almost always invertible. And if you take any random semidefinite program, it almost always has a solution in the interior. But if you take problems that are encoding of some things, you will have redundant encodings and so on. And so in the end, you will get almost always solutions that are on the edge, and then we are screwed. So that's part of the reason why we are not particularly good, I think, on this kind of problems. That's because it's very easy to get some redundancy or so on, and then there is the solution lies on the edge, which doesn't mean there is only one solution because it can be multidimensional, but it lies on some face of the spectrohedra, and then we are screwed.
So this means that other solvers are using other approaches?
Completely different.
Okay.
Things like cylindrical algebraic decompositions are more symbolic methods, not numerical ones.
So.
And if you get if you are using some exact method, that's not an issue for you.
So is there any reason why you're using this approach and not?
Well, because it works on my problems,
Okay.
whereas others don't.
Okay.
Basically, it's simple. If you for this kind of quadratic invariants, if you have only 2 or 3 variables in your program, other solvers will manage it. But if there are a dozen or so, they won't.
Okay.
Whereas it's quite easy with this method. So, and actually, the initial problem is decidable. Real arithmetic is decidable. So these exact methods used by other solvers could be complete, but the thing is that the complexity is so high that in practice, you get timeouts.
What is this table?
Real arithmetic.
Okay.
Polynomial inequalities in real arithmetic. It was proved by Tarski in the mid-20th century. And so you get complete algorithms like cylindric algebraic decomposition, and you manage to compute. But the thing is that it's doubly exponential. So
Okay.
just it works for very small problems, but other than that, it doesn't. Whereas you're doing approximate things with numerical solution, we get you solutions for larger problems, but it's not complete.
Okay. Yeah.
So it's a trade-off. I mean. So just in the end, we have a fully proved implementation using Coq. It's based on a bunch of libraries, including matcomp, flock for floating point arithmetic, this one for polynomials and so on. So a huge lot of dependencies. And the basic idea we implemented what we call a reflexive tactic. So it's a tactic that base the proof on some computation. And this will be the Cholesky decomposition. The way it works, we have some goal we want to prove. Some polynomial is non-negative. The tactic will parse it to read the polynomial and so on. We will get a semidefinite program out of it, call a semidefinite programming solver, retry the solution, and encode a problem, basically the Cholesky decomposition, such that if the Cholesky decomposition succeeds, then our solution is actually a solution. So we have proved the theorem of correctness saying that if this is true, then our polynomial is actually non-negative. And the only thing that is left to do is to do the computation of the Cholesky decomposition and check that it actually returns true. So there is some floating point computation in there. These are the benchmarks, so compared with other things that were either not verified in the sense not implemented in a proof assistant, or verified and implemented in proof assistant. So that's our solution in Coq. This is done in PVS. This is using Coq, and this is using whole light. And various methods. Most of the time is trying to round to an exact solution, because this is very easy. You try to round to a solution. This is heuristic. You don't need to prove anything. You get your solution, and you just have to prove that the two polynomials are equal, and that one is the sum of squares, so it's non-negative. So the proof is like 10 lines in Coq. Whereas ours is a bit more complicated because you have to prove that our floating point computation is bounded and so on. But the results are quite good here. And the last point is that we are doing floating point computation inside Coq, because here we have to compute the Cholesky decomposition to check that it actually works. And we have to do it inside Coq since we rely on this computation to be correct. And unfortunately, currently in Coq, we get only integers that can be computed with the arithmetic unit of the processor, so that are efficient enough. That's enough to do some floating point computation, because the floating point is just a mantissa that is an integer and an exponent that is also an integer. So you can manage to compute your floating point value just with integers. Works perfectly well, but it's slow, like 1,000 times slower than implementing it directly in OCaml or any language you want, and using the floating point unit of the processor. That's what makes the difference. So we'll present it next week at ITP. And we managed to modify Coq to not only have access to integers, but also to floating point computations. And it's quite a bit tricky to do this, remaining sound and not breaking Coq and being able to do proofs of false, because you are computing some value with floating point and another which should be equal, whereas they are not, because they are behaving differently on different machines. A lot of tricky things. That, well, the details are in the paper, but it was a bit more tricky than we expected in the beginning. But it's feasible.
And they assume you can do this without pulling flock as a dependency to Coq?
No. But then if you want to do actual proofs about your floating point computation, it will be much more convenient to use flock. But it's not a dependency of flock.
So you just say, okay, you have two integers with polynomials.
Basically what we did is we need a specification of floating points, values and computation. So we basically copied it from flock, but it's only 400 lines.
Okay.
Whereas flock is many thousand lines with all the proofs and so anything. So we only keep the necessary part of flock, which is really small. That's a specification explaining what's a floating point value, what's an addition, what's a multiplication. And more or less that's it.
So you provide access to native floating points,
Yeah,
but specify them using flock spec.
yeah, basically. And we are both match.
Sure,
Otherwise, everything is broken.
sure.
That's the same for integers.
Star.
Yeah, we'd be interested to discuss. And yeah, that's it. Thanks for your patience. Maybe there was too much thing I tried to put.